Hello, everyone. Welcome back. My name is Professor Andrew Timming, and I am very pleased to welcome you to this third and final lecture corresponding to Chapter 3 of my textbook, Applied Statistics, Business and Management. So you will recall in the previous lecture, we looked at measures of dispersion, focusing primarily on the standard deviation and how to calculate it, and maybe took a few steps in terms of learning how to interpret it. In this lecture, we will look at graphical representations of data, and hopefully by the end of this lecture, you will have a deeper understanding of not only the measures of dispersion that we looked at in the previous lecture, but also the measures of central tendency that we looked at in the lecture before the previous one. So you will recall that the measures of central tendency include the mean, the median, and the mode. So in this lecture, we will focus on what are called frequency distributions. We will focus on histograms and pie charts and other such graphical representations of our data. So without further ado, let us move on. Here we have the textbook that we are using in this lecture series. It's called Applied Statistics, Business and Management Research. You are, of course, most welcome to buy this textbook for yourself, or should you prefer, you are welcome to check out your nearest university library and have a read without charge. I am good either way. The only thing that's important to me is that not only you enjoy reading this textbook, but also that you learn a thing or two about applied statistics after having read it. You might recall in the last couple lectures where I said that rather than jumping straight into carrying out statistical tests, it's important to step back and take stock of your variables individually, one-on-one. And this involves the generation of what we call descriptive statistics. These include statistics like the mean, the median, as well as the standard deviation. Now, another thing that you should probably do before you jump into your statistical analyses is to look at the frequency distributions of each of your variables. And your frequency distributions will tell you something important about the spread of your distributions. All right. So a frequency distribution is defined here as a layout of the total responses for a variable, including how they break down in terms of total numbers for each score and percentages. That's a bit of a complex definition, but don't worry, on the following slide, you will better understand what I mean by a frequency distribution. So if you're looking again at a bunch of scores, a bunch of numbers, it's hard to understand or identify patterns in the data. The problem with raw data is that it's just a bunch of numbers in a column, and they don't necessarily tell us anything just by looking at those numbers. This is especially the case with very large data sets with big samples. So what we want to do in creating frequency distributions is to organize those numbers and scores into counts and percentages that give us a quick overview of how they are distributed. And a frequency distribution can also be converted into a pretty cool graphical representation that we will call histograms. And you'll learn a bit more about a histogram later in this lecture. Okay, so here you can see the frequency distribution of the data set that we've been using over this lecture series. So over the last 2 lectures, we've been looking at a data set of 25 students, 25 respondents, and their scores on a statistics test. And you can see those scores on the left-hand column there. You can see that the lowest score was a 48, a fail. You can see that at the top. And the highest score was a 100%, in other words, a perfect score. And you can see that at the bottom of the distribution. And as you move rightward from the left-hand column, you can see first the frequency. This is the total number of cases that correspond to each score. So you can see that one person got a score of 48, one person got a score of 60, but 2 people got a score of 74, and 3 people got a score of 78. So 3 out of 25 got a score of 78. The next 2 columns over, percent and valid percent, are identical. The reason they're identical is that there are no missing values in this data set. If there were missing values, the valid percent would exclude those missing values, whereas the percent would include them. And these are just the percentages corresponding to the actual counts for each individual score. So 12%, you can see there, corresponds to 3 respondents who got a score of 78. All right, and in the last column, you can see the cumulative percent, and this simply adds up each percent until you reach 100% at the end. So this is what we call a frequency distribution for this variable, and it is reasonably useful to look at it, but perhaps something even more useful would be a graphical representation of this data, and we'll learn more about that in the next couple of slides. 2 of the most common forms of graphical representations of descriptive data include the histogram and the pie chart. And we'll look at each of these briefly now. So a histogram is defined here as a visual representation of a frequency distribution, usually in the form of a type of bar graph. So the previous slide, we looked at a frequency distribution, and what we can do is we can take those data and essentially describe them visually in the form of a histogram. And you'll learn about what a histogram looks like. I'll show you an example in the next slide. Now, in my view, histograms are very useful, more useful, in fact, than a frequency distribution, because a frequency distribution is simply a bunch of numbers, but a histogram is taking those numbers and converting them into a graphic, a visual representation of the distribution of those scores. You'll recall that histograms and frequency distributions are most relevant for ordinal and scale level variables that can be rank ordered from top to bottom. And this is because they allow you to see visually the mean, the median, and the standard deviation. Not very precisely, right? If you want precise information, you're going to have to look at those statistics, the actual number for the mean, the median, and the standard deviation. But if you have a histogram, you can at least get a sense of how those scores are distributed just by looking at it. Pie charts are, I'm sure you've come across these at some point in your lives, circular representations, and they contain a breakdown of scores. Generally speaking, pie charts are more relevant for nominal level variables than they are for ordinal or scale level variables. If you have ordinal or scale variables that are hierarchical, then it makes more sense to generate a histogram, whereas if you're dealing with nominal variables that have no hierarchy associated with them, then a pie chart can be a useful way of breaking down the distribution of scores. As the old saying goes, a picture is worth 1,000 words, and I think that definitely holds true in respect to histograms and pie charts. So in the next slide, let's take a look at what a histogram looks like. Here I've asked SPSS to create a histogram using the data that were reported in the frequency distribution from 2 slides ago. So this is a breakdown of the scores, the 25 scores that we have been using in relation to the statistics evaluation, the test that these students took hypothetically at the end of the semester. And what you can see here is a clustering of scores around the center of the distribution, right? So you can see that around 78%, you have the highest number of individuals. So that's the tall line in the very middle. And then at the extremes, you see far fewer people scoring at that level. So there's one person who got a score of 100. You can see that score at the far right. And there's one person who got a score of, I think it was 48%. You could see that at the far left. But generally, this is creating what we call a bell curve. The bell curve can be interpreted as such. So along the x-axis, you have your scores on the test or on the whatever variable you're looking at. And on the y-axis, you have the frequency or the number of individuals in the sample that correspond with each score. So a typical bell curve is such that most people score sort of around the average. And as you move out to the extremes, to the very high scores and the very low scores, you end up with fewer people achieving those scores. Now, most of our ordinal and scale level distributions will be normally distributed. And we'll learn more about this in the next chapter. In fact, the entire next chapter, chapter 4, is dedicated to this concept. But very briefly, I'll just say that a normal distribution looks like a bell curve, right? Sort of like the one that we looked at in the previous distribution. You can see a sort of bell-looking shape taking form where the majority of cases are clustered around the mean, and as you reach the extremes, both on the right and the left of the distribution, you have far fewer cases. Now, ideally, you want your ordinal and scale level variables to look like a perfect bell curve, but in practice, they rarely do. And in practice, you will find that distributions suffer from what we call kurtosis or skewness, and we'll look at each one of these problems right now. So we'll start with the concept of kurtosis. Kurtosis refers to the extent to which a set of scores is clustered either too close to the mean or too far from the mean. And again, this is only relevant for an ordinal or scale level distribution. So try and visualize for a moment what that distribution might look like, right? Now, it should be obvious to you based on what you've learned about the standard deviation in the previous lecture that this statistic or this concept of kurtosis is related closely to the spread or the variability of scores. So where there is a high standard deviation, where the amount of variation in scores is high, then kurtosis is high. And when there is a small level of spread, when most of the scores are clustered around the mean in a distribution, then the standard deviation is low and kurtosis is low. So high levels of kurtosis are associated with high standard deviations, and low levels of kurtosis are associated with low standard deviations. There are two different forms of kurtosis that can be problematic. The first is what we refer to as leptokurtic distributions, and these are ones that are excessively peaked, right? So a very thin distribution that's very high and very thin. And the second form of kurtosis that is a problem is what we call platykurtic distributions. And these are distributions that are excessively flat. In other words, they're short and they're very wide. So let me give you an example in the next slide of what these types of kurtosis might look like. These are both bell curves of a sort. They appear somewhat normally distributed, but the problem with kurtosis is that although they may appear normally distributed, they're too peaked in the case of the first example here on the slide, or they're too flat in the case of the second example here on the slide. So the leptokurtic distribution on the left-hand side has a very low standard deviation. You can see this because most of the scores are clustered around the mean, and the graphic on the right-hand side, the platykurtic distribution, has a very high standard deviation because you can see that the scores are not clustered closely around the mean, but instead are quite drawn out and highly variable on the right-hand side and the left-hand side of the distribution. So it's important for you to understand that this type of distribution is a problem, right? You want to have ideally a nice bell-shaped curve, and I will explain why that's the case in the next chapter or series of lectures associated with the next chapter. But for now, it's important for you just to walk away knowing that leptokurtic and platykurtic distributions are not ideal, that they are problematic. The second type of problem with distributions, again for ordinal and scale level variables only, is this concept of skewness. So skewness refers to the lopsidedness of an ordinal or scale level variable, right? So they won't look like a nice bell curve. They'll be lopsided, either skewed to the right or skewed to the left. So a distribution that is excessively skewed to the right, also referred to as a distribution that is positively skewed, has a long tail on the right-hand side of the distribution, and this is caused by extreme high scores. So you remember the example I gave in the previous lecture, or maybe the lecture before the previous lecture, about income, right? So if you have 10 people and you ask them their income, and one of those people is Elon Musk, then that extreme score is going to pull the tail all the way to the right. It's not going to look like a nice bell curve. A distribution that's skewed to the left, that is to say negatively skewed, has a long tail on the left-hand side of the distribution, and this is caused by extreme low scores. So if most of the scores are quite high, but there's one that's very, very low, then you'll see a distribution that is negatively skewed or skewed to the left, and this is because the extreme low score is pulling that tail far to the left. So again, this is kind of hard to conceptualize just with words, and so what I've done is on the next slide, I've given you some graphical representations of histograms that suffer from skewness. So let's take a look at them. Okay, you can see here graphical representations of skewness. On the left, you can see what positive skewness might look like. That is a distribution that is skewed to the right. And on the right, you can see what negative skewness might look like. That is a distribution that is skewed to the left. So we'll start with the one on the left-hand side, positive skewness. Here you can see a long tail to the right. And what is happening here is you have one extreme high score that is essentially pulling the entire distribution to the right. Now, if you look on the right-hand side of this slide, you can see an example of negative skewness. And here you have a long tail to the left. So what's happening here is you have mostly a bunch of reasonably high scores on the right-hand side, but you have one extreme low score that's pulling the entire distribution to the left. So as with kurtosis, I want you to understand that skewness is a problem. You won't fully understand why it is a problem until the next chapter, where we look at in more detail at the normal distribution, at the bell curve. But for now, I want you to understand what causes positive and negative skewness, and that positive and negative skewness are problems. That ideally, when we're dealing with ordinal or scale level variables, we want nice bell-shaped normal curves. Now let's take just a brief moment to summarize what we've learned over the last 3 lectures. So these corresponding to chapter 3 of the textbook. We've looked at descriptive statistics and how descriptive statistics describe one variable at a time. And in particular, we focused on a series of descriptive statistics that can be described as either measures of central tendency or measures of dispersion. So measures of central tendency include the mean, the median and the mode, where the mean is the arithmetic average, the median is the exact center of a distribution, and the mode is the most commonly found score in a distribution. We've also looked at measures of dispersion, so these are measures of the extent to which there is variability or spread of scores across the distribution, and the ones that we've looked at are the range and the standard deviation. And in this lecture, we've looked at frequency distributions, the breakdown of the counts of individual variables per each category, and histograms are essentially graphical representations of frequency distributions, as well as pie charts, which are more relevant for nominal level variables. And we've also very briefly looked at the concepts of skewness and kurtosis, where skewness refers to a distribution that is excessively skewed either to the right or to the left. In other words, where extreme scores are pulling the distribution to the right or to the left. And kurtosis refers to the excessive peakedness or flatness of a distribution. At this point, before you move on to the next lecture series, I would like you to stop, press pause, and answer these 6 questions. These will help you better digest the information that was presented over this lecture and the previous 2 lectures. And this brings us to an end of chapter 3. I hope you have enjoyed learning about descriptive statistics and graphical representations. And I look forward to seeing you in the next lecture series, which focuses on the normal distribution, where we'll go into a little bit more depth over the concepts that you've learned about in this lecture. See you soon. Bye.